Hi, I'm Roy Barkan, and we're going to talk a little bit about ranges today. I hope you had a good time in the last 2 days of the conference. It was really thrilling for me. I really enjoyed it, and I hope everyone else did as well. And let's try to end it with a bang. So as mentioned, my name is Roy Barkan. I live here in Tel Aviv. I've been doing C++ for quite a long time now, and for the last 13 years or so, I've been working for Istra Research. We're a low-latency trading company based in this area, and we're always looking for great C++ people to do interesting and hard challenges in terms of low latency, very scalable code, statistics, academic stuff, etc. We're not tons of people here. I can see all of you. If you have any questions, please raise your hands. Let's make this interactive. Okay, so we're going to talk about ranges today. The ranges library is one of the 4 additions that we got in C++ 20. I assume most of you have heard of ranges already. This is sort of not an introductory talk, but a more advanced talk. But I'll still try and give you a short sense of my perspective on why this library is such a great addition and why it's so cool. And I'll give a quick overview of what we already have out of the box. And then we'll dive into what it would take for us to write our own range adapters, which I think is something that can be very cool and very helpful in our day-to-day work. And then we'll also take one example, one case study, and try to reason about that to actually make sure that we understood all the theoretical details. Okay, so the main thing about ranges, from my point of view, is the point of composition. The ranges allows people to write algorithms to break them down into different building blocks that compose. As mentioned, C++ 20 gave us ranges, concepts, coroutines, and modules. Those are the big 4 for C++ 20. And the ranges library was very new, but on the other hand, it rests on a lot of foundation, on a lot of background. C++ 98 already had iterator-based library with containers and algorithms, and we all know about it, hopefully. And the ranges library doesn't mean to totally deprecate the iterator-based stuff, just to augment it and make it better. There's been a lot of work in terms of building composable range-based algorithms and building blocks on other programming languages, such as functional and vectoric languages. I myself have quite a lot of background in the R programming language, and you can see presentations by Conor Hoekstra about various other languages where ranges are used commonly, and get inspiration from those types of talks. And there are also quite a lot of similar languages to C++ who've been to the ranges game earlier than C++, such as D, Rust, and Java. They had ranges libraries even before we did, and the standardization committee had the opportunity to learn from their mistakes, to learn what they did well and not well when they came in and added ranges into the C++ language. And when I say that composability is the main innovation, first and foremost, I mean that the input of one component in a ranges library is just the range, and that's also the output, and that means that I can break things into pieces and connect them piece by piece. There's also this very important notion of range adapters, which are these ways to encapsulate like ideas or algorithms or flow diagrams of algorithms into specific objects and specific variables, and we have this sort of like a dynamic where an object or a variable, we can sometimes look at it as a variable with an address that we can pass around, but sometimes we also can think of it as an algorithm, as a higher order type of object. And many times when we compose these building blocks into one larger type of scheme or flow diagram, these things are called expression templates, and we'll see what those are. And the last piece of innovation in the ranges library that helps with composability is the new notion of projections. And projections are just typically very small alterations that the existing building blocks that were given to us can do on the objects that they work on in order to better fit one into another. So if I have several building blocks that I want to compose together, but they don't fit precisely well, sometimes projections can come to the rescue and help us. So we want to dive deep into the library. So let's start with like a dictionary and some terminology. So what is a range in C++? In C++, a range is just an abstraction over just a sequence of elements, okay? So whenever we have elements that have a beginning and an end, that's a range for us. It's very, very similar in notion to the sequences that we had since C++ 98, but now we call them a range. Instead of having two iterators, like beginning and end, we have just one range, and that range has an iterator and a sentinel, okay, where the sentinel is an abstraction, it's a more general a way to think of the end of a range, okay? So if we want to know if an iterator is at the end of a range, I compare it with a sentinel, and the sentinel itself doesn't have to be another iterator, it can just be a different object, but that's the way it is. And then a range algorithm is basically just a function that operates on ranges, okay? So one of its inputs typically is a range, its output is typically either a range or an iterator, and sometimes its output can be even more complex. And there are sometimes range algorithms that operate on their input ranges in place. So they receive a range as an argument and change it as they work. What's a view? A view is a special type of range, okay? So if anything that is a sequence of elements is a range, a view is a very, very specific type. And the only thing that's special about a view is the fact that it's cheap to pass and to hold, okay? So a view is something that if I have a view in my hand, I can pass it to someone else, and it will always be cheap to copy or cheap to be passed. So if the view itself, it has to be movable, and the move operation needs to happen in constant time. And it also, it doesn't have to be copyable, but if a view is copyable, then the copy operation needs to take place in a constant time. Okay, and later on we'll understand why this happens. And we should note that when a compiler sees our code or our classes, it's not easy for a compiler to know what is cheap and what is not cheap, what might happen at constant time and what might not. So whenever we write our own class that is a range, and we believe that it's a view, and we know that it conforms to the view requirements, we need to opt in. We need to tell the library this type is not just a range, it is a view, and we use the enable view specialization mechanism to do that. So we specialize enable view for our range, and if we say it's true, then it's true. We are a view. Okay, what's a range adapter? A range adapter is basically something that manipulates a range, okay? So it's sort of like an algorithm in concept. It's something that it will take an input of one or several ranges and potentially more arguments, and its output is one single range. But the thing is that they typically do their work in a lazy fashion. It's not like when I create the view or when I take a range and I apply an adapter on it, the act of creating the adapter doesn't really do any meaningful work. It's just that when I can use the adapter typically as a view to iterate through its elements, and as I iterate from beginning to the end, that's when the actual work of the adapter takes place, and we'll see an example in the next slide. The main thing about adapters is that they are meant for chaining, okay? So it should be very, very easy and very, very I guess, intuitive to take several of these adapters and compose like a complete flow of information using those things. And this composition, it's important to make it so easy and seamless, and that's where the notion of the cheapness of views comes into play, because these adapters many times will create them on the fly, they'll be moved, destroyed, etc., and we don't want to think about their performance costs. So when we use views, we know that things will work out for our best interest. Okay, so a few examples about the composability, so we'll not just be talking up in the air. So first of all, algorithms themselves, more composable in ranges compared to C++ 98. So for example, the search algorithm takes two ranges as inputs and returns a range as an output. And because the output of a search is range, I can pass it directly into reverse. And so if I would run this type of code, we will look for the first instance of ABC inside an input string. Once we find it, the search operation will return a range of this location where ABC is inside str, and reverse can go ahead and reverse it. Okay, so that's one notion of composability. The next is, again, has to do with the views and the adapters. So Here we can see the use of the split adapter and the take adapter. And they basically do what they sound. You might have seen those things in other languages as well. And we use the pipe operator here to compose the different adapters. So we take some input range. We use an adapter of a split, which converts it from a range of characters into a range of ranges of characters. Okay, we split it by space. So for example, if str was a sentence, split will create a range of words, and each word is a range of characters. And then take two will just take the first two elements out of that split. And in the ranges land, things are safer than typical C++ fashion. In case the result of the split operation will be less than 2 items, take two will just return a result in fewer than 2 items. It's not undefined behavior to ask for more elements than what's going to happen. And as we mentioned, this thing is actually very, very lazy. The fact that I've created this chain of objects actually didn't really do any meaningful work and didn't even try to start looking at the str range. Only once I try to iterate over elements, that's when the operation and the work takes place. And then we can also create chains that do not start with a range. Okay, so let's look at this pipe or this sequence of 2 adapters, the filter and then transform. Okay, so the filter takes every element and converts it to an int and checks if it's even. And transform goes and squares those results. Okay, this is all you can see. The auto argument here. This chain of things can work on either a range of integers, a range of longs, a range of doubles, etc. It will all work. And this square evens thing is, you see, it's a variable, but when I think about it, I don't think about it as data. I think about it as an algorithm. Okay, it's something that I can pass around as an algorithm, and it's sort of like, you know, a chain of operations without its start. And whenever I want, I can tack on this thing at the end of an existing chain that already has a range and start iterating through it and get the results. And again, sometimes even simple combinations can really enrich our vocabulary. So sometimes if I want to, you know, talk with other people about certain building blocks or certain algorithms that I want to write, I can do it without even writing a function declaration. Okay, so for example, if I want to take a series of input elements and break them up and create a histogram, assuming that series is already sorted, then I can just, what do I need to do? I need to chunk the series based on the equals predicate. So every consecutive equal elements will be chunked together. And the result of this chunk by will be a range of ranges where in each sub-range all elements will be equal. And then this transform operation will take each of those sub-ranges and convert them to just a pair of 2 items. The first item is the representative of that sub-range. The second is the length, the number of elements that we had. So this histogram thing, I can tack it on any range that I want, whether a range of integers, a range of strings, etc. And the result of that will be just a histogram of item after item, where each item is sort of like the result of unique minus c, if you know, like one representative of each item and the number of occurrences that it happened. Okay, so I wrote a new algorithm without even declaring a function. So that's composability for us. So when we got the ranges library, it wasn't just a set of concepts and notions. We also got actual concrete range adapters, which are views that we can go and use right away. We got a very large number of views in C++20. A big number were added in C++23, and more are planned for C++26. There's a whole plan. I won't really go over each and every one of them, but there are some extra information. There is some extra information in the slides. Once you download them, you can take a look. And basically, just to try and organize our thoughts here, I broke them down into several groups. And this breakdown that I did, I think it can be helpful for you as well, was based on sort of like the shapes of the ranges that these different adapters work on and what they do to the shapes of the ranges. What do I mean when I say a shape of a range? Sometimes people refer to this notion as the dimensionality or the dimension of a range. So just a single set of items is a one-dimensional range. But if I have a range of ranges, I can think of it as something of rank 2 or 2 dimensions. Okay, so a 2-dimensional a range of ranges is something that's 2-dimensional. And there are some operations that I might do that take a range with some number of dimensions and increase the number of dimensions or reduce it. Okay, so factories are those views or adapters that start with nothing and just create a range. Okay, so they start with 0 ranked view and create a range of rank 1. Okay, so the empty adapter will create just a range with 0 elements. Single will create a range with 1 element. Iota creates consecutive numbers, so we can start with a starting number and tell it when to end. It can even never end at all. And then there's repeat, which takes an element and repeats it as many times as we want. And then C++23 also adds generator, which starts with nothing and creates a range. Rank preserving, I'll take something that already has some rank, and my result will be of the same rank, of the same shape. So most typically, transform is what we think about when we discuss shape preserving adapters. Basically, each element goes through a transformation. The result is the exact same shape as the input. Even the number of elements is the same. And note that even filter is a range that, from my perspective, keeps the rank, keeps the shape of its input, because although a filter will typically have fewer elements than its input, the shape is still the same. Okay, if I had a one-dimensional thing, after a filter it's still one-dimensional. If it was two-dimensional, it will keep being two-dimensional, etc., etc. So again, I won't go over all of them, but if you have specific questions about one adapter, you can raise your hand and I can talk. Yeah, go ahead. So the question is whether all is rank decreasing. I'll actually have quite a few slides specifically about all, but briefly I'll say that no, all keeps the rank, but we'll see it. With C++, we have another type of quirk related to dimensionality, which is the fact that if I wanted a two-dimensional range, like a range of ranges, that one of the dimensions can either be compile time known or runtime known. Okay, so I can have, for example, a range of tuples of 3 integers. Okay, so each item is a compile time known tuple of 3 integers. Or alternatively, I can have just a range of ranges of integers, where each of the sub-ranges, I don't know upfront its size and its dimensionality. Conversely, if I look at the input, there's also the option of taking some extra dimension as just variadic arguments. So for example, the zip adapter basically keeps the shape of its input as the output, but it changes from variadic into tuples. So I take a variadic number of ranges, like a range of integers and a range of doubles and a range of strings, and I create an output range of tuples, where each element of the tuple is an integer, a double, and a string. Okay, I hope that makes sense. So we have all these very, very large number of basically tools in our tool belt that we can use, and we can also compose them. That's again one of the superpowers of the ranges library. I won't go all of them one by one, but again, as you mentioned, there's details. And now let's talk a little bit and dive deeper about what does it mean to write our own adapters. How does one go ahead and write their adapters? The key is to know what we want to do and also to play well with the rest of the ecosystem. Because if I want to my own adapter to be used and composed with everything else, I want to play well, right? So first of all, I should note that adapters, they support this nesting operation, and I've already shown you the pipe operator, but actually both pipeline and infix composition is allowed. So it's exactly the same to write the first and the second lines here. We'll generate basically the same code, and you can judge for yourself which is more readable, whether to go with the infix type notation, or with the pipeline notation, where you can see that a split takes 2 arguments, and with the first version, the first argument and the second are all within the parentheses, and in the second version, the first argument comes to the left of the pipe, and the second argument comes in the parentheses. Similarly, the take view also takes 2 arguments. It's either the split view and the number 2, either before the pipe and inside the parentheses, are all the same. And then there's the term range adapter closure. Sounds a little scary, I know. What is a range adapter closure? All it is, as I mentioned before, it's just a chain of operations, maybe even just one element in a chain, that doesn't start with a range, okay? That's the thing that we can tack on to a range later on, okay? So that's called the range adapter closure. And the thing is that these are objects that their only existence, their only reason to exist is to be chained later on to some range, and so we can start iterating through it. And semantically, when I see a range adapter closure, I basically think this is an algorithm, not a range. And typically, when I want to write an adapter, what I want to write is a range adapter closure. Okay? And happily, the ranges library came to our assistance, and they gave us this class in the standard, which uses CRTP style of generic programming. It's called range adapter closure, to help us deal with all the complexities of writing a range adapter and help us deal with this duality between nesting and pipelines. So every range adapter closure needs to handle both nesting or infix notation as well as pipe notations, but I don't have to write it myself. The range adapter closure object in the standard library helps me if I just use CRTP correctly. So here we go. There's our first class of the day. This is the first range adapter. So what's first? First is a range adapter. I can tack it onto a range, and I get just the first element out, okay? And if the range that I tack it on is empty, then tacking it first will just do nothing, or we'll keep the thing empty. Okay, so here's my first implementation. There's a link to GoBolt here if you like. And the entire range adapter is just 4 lines of code. I create my struct, I use CRTP style inheritance, and all I need to do is implement the call operator that accepts a forward range as an input. And if I can do it at const per time, I might as well declare this as const per. And in this case, as you mentioned, all I want to do, all I need to do is just return the subrange. I take the input range as an argument. I need to return the output range as a result. In our case, all I want is to return the subrange that starts whenever the input starts, and either ends exactly where the input ended, if the input is empty, or just one step forward to encapsulate the fact that we're just a single element of the entire range that was given to us. Okay, and this class is a class, but I actually typically in the ranges that I don't expect people to create instances of this class. I create an instance for them. I create a global variable, a global context variable, typically called with lowercase letters, called first. And the way that people would use it is to just tack on the first, either with infix notation or with pipeline notation, to their own ranges, and this code works. But it's actually very, very unsafe to write an adapter this way, and I would not want to push this into production. Does anyone have any reason or thoughts what's wrong or what might be bad with this implementation? Okay, so the issue is actually with these ampersands here, where I basically agree to take an input range either by value or by reference or by R value reference, and the range, when the call operator gets called, it will the range might get destroyed immediately when right after the result is created. Okay, and the subrange object is something that exists in the standard library, and I can return it, but its own semantics is not lifetime preserving in any way. So once I create a subrange and I give it 2 iterators into some other range, if that other range gets destroyed, subrange will not know about it and will keep pointing or have dangling iterators into that destroyed place. Okay, and that's the reason why I actually performed this pipe operation right inside the print line, and I didn't try to tack it on to the AutoX declaration, because if I would have done that, things would have gone terribly wrong, because as mentioned, these pipe operations, they basically are application of like a chain of calls to a pipe operator, which creates temporary objects and destroys temporary objects. So as I create one pipe after another, I create more and more complicated chain, but the intermediate results get destroyed. And if this first element had iterators into some intermediate results that got destroyed, then things can go very, very wrong. Okay, so that's why we need to deal with dangling things a little bit better. Okay, so as mentioned, the chains involve the creation and destruction of many, many temporary objects. By the way, this has nothing to do with the infix notation or the pipeline notation. In both cases, when we have these chains of function calls, one into the other, like all temporaries in the way, they all live until the semicolon, but once the semicolon arrives, all the temporaries get destroyed. And the solution is to try and have like an aggregation. So whenever I create an object in the chain, that object isn't only in charge of itself, it's also in charge of keeping hold of whoever preceded it. So if the input range that I get, if the other range that I get as an input is temporary and might be gone, I'll be able to keep track of it and hold it, so it won't be gone. I'll have one less chance to keep it alive and not have it destructed. And obviously, I want to do this all with best performance and not use any mechanisms like reference counting, etc. So if I create a string and I pipe onto it a split view, and I pipe onto that a take view, the type that I basically have in my system is this variable who's like a very, very complicated template. It's a take view of a split view of a string. So this object basically can keep hold of everything inside it, and that way the string is still can keep its its existence alive. And the adapters themselves, each of them is typically very, very small and cheap. So taking an adapter and passing it from one temporary to another and building these compositions out of it is very, very cheap. So we don't really care about the fact that the creation might be complicated. But the start of the chain, the range of the start of the chain, that can be sometimes expensive. And that's why we coined the term view. Okay, a view is something that we know is not expensive. And that's why we want all these chains to start off with views and not with ranges. So we don't feel any remorse or any pain if multiple temporaries containing those objects might get created. So before I use that information to write an actual first adapter that works, I want to take a quick digression and tell you a little bit, like I said before, that the best implementation, I think, of the first range adapter, if I needed to write a first range adapter by myself, I wouldn't write any class. I would just create a constexpr variable called first, which is just take one, okay? Take one, take the first element of a range. And this is just as good as any range adapter that I would write, much, much safer, much, much cleaner. But this is not what we're here to talk about. We want to talk about more complicated cases where we can't just, compose things that already exist. So let's write the first range that really works and is, I think, production grade ready. So as you see, it's a little more than 4 lines of code, but it still fits into a slide, a little dense slide. So let's try to go over it and understand what we have here. Okay, so basically we have declared 2 classes, or one class and one struct. It's the first item view and the first itself. The first is very, very similar to what we've seen before. And the first item view, as mentioned, is this view object that we'll use instead of the ordinary stood subrange that we had before, which didn't hold on to its input. The first item view will be able to hold on to its input. Okay, so it has a member, which is the inner member that it can hold on to. Okay, so that's the way it is. Again, writing this view is not so complicated. And the reason is, again, that the library came to our assistance and gave us another CRTP helper called view interface. So if I use CRTP to take view interface, I get a lot of things for free. I don't need to implement a lot of things. So I just keep hold of this inner object so it won't get lost, won't get destroyed. And in my constructor, I receive it and I move it in, make sure I get a hold of it. And basically, in our specific case, all we need to implement is just 3 member functions, begin, end, and size. Okay, begin and end, very, very similar to those arguments that we gave the subrange before. It's the beginning of the inner iterator, and either the beginning or the following item in the inner iterator, based on whether that inner one is empty. And the size that we can expose is either 0 or 1, based on whether the inner argument is empty. So this is our first view that we wrote, which can actually work. And now there are 2 extra lines here before going and implementing struct. Does everyone know what these 2 lines are? Those are an addition that we got in C++17 called class template argument deduction, right? CTAD. And basically this is a way to tell C++ compiler that when I want to create this template class called the first item view, I don't need to specify the exact template arguments myself because I'm giving a hint to the compiler how to use it. And this hint is something that's a little more complicated than maybe you've used to seeing, because this deduction guide is templated on forward range, but the filter view that it creates is a filter view on views all T of range. That has to do a little bit with Ophik's question before, so we'll dive into that a little later. Once we have this first item view in hand, then it's very, very easy to implement the struct first. Again, very, very similar to the way we did it before, but the call operator, instead of returning a subview, will return the first view item. And I think maybe the forward needs to be in here and not in here, but basically this is slide code. Hopefully Godbolt works if you go and look at the slides later. So this is what we have. Let's make sure that we didn't miss all the important parts. So I marked the important parts. Try to see that you understand what I mean with them, and if you have any questions, I'd be happy to answer it. But again, I'm using C++ 20 concepts to say that my view can also be tacked on to another view. I can't be tacked on to a range or to anything else. I use the CRTP interface. As mentioned, I keep hold of the inner item, move it inside, and I need to implement begin, end, and in our case, in this specific case, I also want to implement size. Sometimes you don't have to. Sometimes the view interface can do it for me. And then there's this trick with Alt T where you can see that the input of the deduction guide is not a view. The input of the deduction guide is a forward range. So there are potential ranges that can fit the deduction guide, but do not fit the class. Okay, and this all view or views Alt T is in charge of converting. If someone tries to create a filter item view with a forward range, then this deduction guide will get some help from Alt T to convert the forward range into a view, so I can instantiate the first item view indeed with a view as its inner argument, as not with a forward range, and we'll see a few slides about that later on. And then, as mentioned, the call operator of the range adapter closure basically returns an instance of that view that we said before. Questions? Yes?
Why do you need the no unique address?
Okay, the question is about no unique address and why do I need it? So basically, I don't have to use it, but it's quite common because, as mentioned, many times these inner objects relatively small, and sometimes people have views that maybe or adapters that tack on several of these adapters one next to another. Consider, for example, like a zip view that wants to zip an iota together with a range of names or strings. So the iota can potentially be a very, very small size, etc. So maybe this no unique address is just a way to tell the compiler that I don't care if, in case the inner is 0 size or has no members, we'll not get a unique address. More questions? Yeah?
So the view, holding the view protects the actual item from being released?
Yeah, when I get a view as an input, it gets forwarded into the constructor of this first item view and gets and moved as a member of this first item view. And that way, even though the temporary get destroyed, the actual item or the actual data actually moved in to the next item in the chain, to the wrapping view, which can hold the data.
So there's a small overhead for holding the view because it's somehow...
Yeah, there are, during the creation of this chain, there are quite a few move operations that take place, and that's a small overhead. And the reason that we use views and not ranges is to make sure that the overhead is small. Cool, yeah?
Can you go slower?
I can try to go slower, but I don't have a lot of time, so I'll try to get slower. Maybe I'll skip a few sections. Okay, so basically we talked about all of this. So in the interest of time, I'll skip it and let you look at it a little later. I'll just mention that const correctness when it comes to begin and end and with views in general is a very tricky subject. And there are many people who think that the committee got it wrong with the way that ranges correctness is done, but I won't talk a lot about that. But you feel free to go and watch Nico Jusutis' talks about this. And And then there are also other tricks that can be done in the deduction guide, not just using the Alt-T thing. So potentially, if we have like, want to compose a reverse adapter over another reverse adapter, there's a trick that actually is mandated by the standard for the CTAD, the deduction guide, to try and eliminate both. Okay, so reverse of reverse is basically nothing. The compile time has to be eliminated. Okay, so views, colon, all, and Alt-T. Let's talk a little bit about that quickly. So again, as mentioned, we have a lot of range adapters and temporaries that get created, and the chains have to outlive their base range. The library uses the notion of L value versus R value to understand whether something is about to get destroyed. Okay, this is basically a common thing in the C++ world, where something that's an R value, something that's considered as an object that might get destroyed very, very soon. So I need to take ownership of whatever it has there. Sometimes this analogy is not 100% perfect, but that's the way the library works. Basically, the library implemented two types of views that can be used in order to deal with lifetimes. The first is a ref view. What's a ref view? A ref view is basically very, very similar to that a sub-range object that we've seen before. It's just a very, very small adapter that holds two iterators, or maybe one iterator and one sentinel, into another view. In case I know that my input is going to live for a long time, because maybe it's an L value, all I need is a ref view, and I can create my own object using ref views. There's no concern that this object might get lost in the way. But if I want to keep control of something, I can use an owning view. An owning view is something that's templated on a type of a range and actually takes hold of that range. It's not copyable, it's only movable. And the move operation is very, very fast, similar to unique PTR, okay? So that's the idea of an owning view. And this adapter called views, colon, all, which is the same as just calling the constructor of all underscore t, can be, when you apply it on a specific range, it can have one of three different types of results. Okay, so if RNG itself is already a view, then calling the adapter views, colon, all, or creating an Alt-T of that view simply returns it as it is, no change. Okay, if RNG is an L value, it means that this L value is going to stick around for a long time, and I can create a ref view that points to it. And otherwise, I'm getting an input that might get lost. So Alt-T is in charge of creating an owning view, taking control of the object, moving it out of the input, and now this Alt-T is basically an owning view that holds the object. Okay, and it's very, very common for, I think, all range adapters in the STL to use views, colon, all as the mechanism to assist them to make sure that things will not dangle or reduce the risk of dangling. So let's go over a few examples just to get a sense of it. So a string is not a view, right? Because its copy operation is not constant time. It can take time. Move is cheap, but copy is expensive. String piped by all is a view, because the work of piping something by all basically it turns it into a view. What kind of view is it? It's an owning view, because the string is a temporary. Okay, it's an R value. If I create a string already that outlives my pipe, then again, the string itself is not a view. If I pipe it by all, it becomes a view, and the type is of a ref view, okay? Understood? Let's get a little more complicated. If what I have is already a view, X is already a view, I already piped it through something, then it is a view. Piping it by all is just as doing nothing. It's the same as doing nothing. And note that this is all like the compiler doing its best, but it doesn't really know everything. And for that reason, for example, stud colon array is something that is not a view because it's expensive to copy and also expensive to move. If I pipe all into it, it's an R value, right? It's a temporary, so I can convert it to an owning view. And that owning view looks like it's a view, but we know that an owning view that holds inside it 4,000 bytes or more will not be cheap to move. Okay, so it's a view, but it's not really cheap to move. So I'm not sure if it's exactly even defined behavior to use this as a view inside the ranges library. Okay, so be careful about arrays. Great. So now let's talk a little bit about the heart of writing range adapters. We wrote basically the wrapper, the adapter itself, but the first example, I didn't really do anything lazy. All the work that I needed to do, I did it when calling begin and end. The typical range adapter actually does a lot of its work in a lazy fashion, basically by creating its own types of iterators. Okay, and most of the work is done inside the iterators. For the transform adapter, for example, it has a special iterator where the only special thing about it is the way that it implements its dereference or star operator, right? So when I dereference the iterator of transform adapter, it will dereference the underlying range and then perform some transformation and return the transformed results, right? Similarly, the filter or stride or reverse adapters, they don't touch the dereference operator. Their main work is on the plus plus or minus minus operators. They basically change the way plus plus works, right? So plus plus on a filter view might actually perform several plus plus steps on the internal view that it had to work with, okay? And then take while, for example, that just takes elements until some predicate happens. It's the only operation that it needs to specialize is that not equal operator between an iterator and a sentinel. So take while, its iterator is exactly the type of iterator of its underlying range, but it has a special sentinel. And its special sentinel, when you compare things to it, will actually call that predicate to make sure, hey, did we take do we need to keep taking, or are we done? Okay? And then chunk and split, they need to change both the dereference and the plus plus operators, and you can think of many other cases where you need the more complicated adapter you need. You might need to change more operators or of the options of the iterators that you implement. And the lazy approach, the reason that we're writing these things, it has a lot of benefits. First of all, we pay only for what we need. If we don't need to complete the entire iteration, we don't need to pay for actually doing all the work for the entire range. This gives us inherent support for infinite ranges if we want. The fact that a range can be infinite doesn't mean that we iterate over it infinitely. And then the fact that several adapters, several operations that happen on the information happen as we move through it means that most of our algorithms and most of our work can be done in a single pass instead of performing several operations by doing several passes over the data, which can be better in terms of RAM, better in terms of cache locality, etc. And then the fact that we're using these expression templates, these compiler knowns special types that are the combination of a transform and a filter and take while, the compiler knows about it. It can create a specific type exactly for our need. And for that reason, there's a better chance that the compiler can inline things and can give you the best performance, like fuse the loops, fuse the operations, etc., etc. So any questions about writing iterators? I'm not going to dive a lot into them because actually there's been plenty of talks, and I really recommend this talk by Barry Revzin. Actually, 2 talks. This is, if you go through these 2 links below, each of them is 90 minutes of sheer joy on iterators and how to write them and the complexities of writing the iterators correctly. But one thing that Barry didn't talk a lot much that I will mention is these 5 lines, all these using lines right at the start of the declaration of the iterator, which basically tells us what the iterator concept, iterator category, reference, etc., of the iterator. And those are ways for me, when I write my own iterators and views, to communicate with the rest of the library what and how my iterator works. So let's talk a little bit about that. So every range belongs to a category, and those categories can also have refinements. So the categorization basically is done based on the power of iteration. It's very, very similar to what we had in C++ 98. I don't know if people remember or know that C++ iterators, there were output iterators, input iterators, forward, bidirectional, random access, and in C++ 20 we got continuous. So this is a way that for compilers to know at compile time what operations are allowed and legal for different types of iterators, and is it okay once I move forward in a range to also keep pebbles or remnants or copies of iterators that have already traversed or not, etc., etc. And very, very similar to C++ 98. ranges themselves also have these types of categories, and every range needs to know its own category. And when I try to compose ranges, every range can optimize itself based on knowing the category of the ranges that come before it, and it can publish, if it publishes its behavior correctly to the ranges that come after it, it can give you better results and better performance. And similar to C++98, the way to do it is by opting in and declaring my own category. The compiler itself doesn't easily or doesn't automatically know my type, although it tries to guess. And on top of the power of iteration, ranges have some additional refinements that can be added to them to, again, tell the compiler something about this range, and it's totally orthogonal. So one is a borrowed range. A borrowed range is a range where I could tell the compiler, hey, you should know that if you take iterators from my range, like the begin or the end or anything, and the range gets destroyed, it's fine. The iterators are still fine. They're not dangling. They're still valid. And if I know that my range is like that, I can I need to opt in by telling the compiler using the enable borrowed range. An example of this of a borrowed range is a string view. Okay, a string view, even if it's destroyed, the iterators are into an existing ring. Sized range is a range where I can know its size in constant time. Basically, so I don't need to check how long it is by traversing from beginning to end. I can ask it what its size is. And here, the CRTP type will try and give me a size automatically and opt me into the size range concept if it knows that there's a way to dereference or to decrement and check the difference between iterators. So if it's okay to take two iterators and perform the minus operation on them, then the library assumes that the range is sized, and I can opt out if I want to. And then a common range is a range with begin and end are the same type. Sometimes it's helpful if you want, especially if you want to call C++98 algorithms on this range. And then a constant range is again a range where the range itself is sort of like a reference to area of elements. The fact that the range is constant means that I cannot change the range and where it points to. The constants of a range, similar to the constants, again, of a string view, doesn't really, or of a pointer, doesn't really change whether the items themselves can be changed or not. So a constant range is a refinement that I can opt into to say and specify that, that the items themselves are constant. And as I mentioned, range adapters must correctly publish their effect on their input, so they can check what categories, what refinements exist for our input, and need to publish what their effects are. So the motivation for that is doing algorithm selection. Let's talk a little bit about what algorithm selection is. And the idea is that if I want to write an algorithm and I have a goal, I can sometimes implement it in different ways based on what I have as an input, how strong my input is. So for example, here are two different algorithms inside the ranges library. One is called size, and the second is called distance. Okay, size and distance, and I copied their description from cppreference.com. You can see that they're very, very similar. They take as input as a range, and they return a signed integer that represents the length of the range. Okay, but size calls it the size of a range. Distance calls it the length, but actually it's the same. What's the difference? Okay, the difference has to do with algorithm selection. Size only works for sized ranges. If I try to give a range that is not sized to size will not compile. And on the other hand, if it does compile, I know that it will run at constant time. Distance, on the other hand, is more flexible. You can give it any range you want, at least a forward range, I think, and above. If the input range is sized, distance will work at constant time. If it's not a sized range, it needs to iterate and go through each item. Distance will do the extra work, but it will compile. Okay, so that's the difference. And Ben Dean has a recommendation to try and use the more generic approaches if that's what we want. Okay, and the library uses concepts as a way to constrain these algorithms. So if I have several algorithms, I can use concepts, again, we're adding C++20, to specify and tell the compiler which of the different implementations to choose based on the types of input that I receive, okay? Before C++20, there were other mechanisms to do algorithm selection. I don't have time to talk about that, but if you want to catch me later. And now I'll take a don't have time for much of a derivation, but I just want to say that sometimes when I create these chains of operations and things look quite lazy, and when I iterate over a range to try and get a histogram, it would seem that I can do this operation of chunking the histogram or chunking the input range by equal elements and then getting the size of each of them or getting the distance of each of them. But again, the distance can sometimes take extra time. So while this operation might look like something that can be done in a single pass, if the input range happens to not be sized, distance itself can take some time, and this operation will still be linear, but it will actually require 2 passes over the input and not just 1 pass. Okay, that's because subrange itself, which is the result of chunk by, might not be sized. Okay, so this is a little bit into the weeds, so I won't talk a bit about that more. Okay, cost correctness. Again, Nico Jusutis has plenty of talks about the harshness of cost correctness when it comes to iterators. Again, because they have indirect semantics. Every range that we write, every range adapter that we write, potentially we want to implement not just begin and end. We can implement C begin and C end in order to create const iterators for whoever wants to use us, and those will apply deep constness. And it's quite common that we want to do it. Again, we want to avoid the code duplication. Happily in C++23, we got this nice adapter called the basic const iterator, which can take a non-const iterator and expose only the constness out of it. So sometimes people can use it. Views themselves are notoriously tricky when it comes to const correctness of themselves and of their iterators. And the basic reasons for that, there are several ones of them. First of all, it has to do with caching. Okay, sometimes, for example, the begin call of the filter iterator needs to do some work, and the standard wants this work to not happen too often. So the call to begin needs to cache some items and do some caching, and caching changes the state, so caching cannot be const. Another thing has to do with this owning view versus ref view. Owning view and ref view, they're both the result of calling all T, but obviously a const owning view cannot really change its elements, but the const ref view can change its elements because it's just a reference. Again, see Nico for more details. A part of implementing the star operator, the not equals, the plus, minus, minus, etc., there are 2 other interesting functions that one might want to implement for their iterators. One's called iter move and the other's called iter swap. I don't want to spend too much time on them, but you can feel free to go and see Jacob Rice's talk about that. And the typical way to implement it is what's known as hidden friends. Those are friends of the iterator, friend functions of the iterator that are declared inside that class, and the stud : ranges : iter underscore move and underscore swap knows to find those inner friends and call them. Those are called the CPOs, customization point objects. That's the best way so far that we've learned to allow different objects that need to use libraries to expose operations to the libraries in a safe manner when those operations are not just simple operators like operator star and not equal, plus, plus, etc., etc. Okay? So any questions about iterators? Great, I won't talk about CPOs either because I want to give just time for questions. And I want to talk a little bit about my own case study, which was trying to create views for sorted ranges. Okay, so I want to create some views when the inputs are sorted and the outputs are things that can be done only when the information is sorted. So for example, merge or set union or set intersection or set symmetric difference are algorithms in the STL that can work in an eager fashion, but actually those are all operations that can be done in a lazy fashion, step by step. If I have 2 sorted ranges, I want to generate just the set union or just the merge, I can do it one by one in every plus plus operation. And if I want to even merge more than one ranges, I can do that using some heap or priority queue data structure. As mentioned, STL has these operations algorithms, but not as range adapters, although they can be done in lazy fashion. Ranges v3 has a lazy implementation for set union, intersection, and difference, but not for merges. And those take 2 input elements. And let's talk a little bit about what it would take for us to implement these types of ranges. So the basic idea is generally, every STL algorithm that works with an output iterator generally works, it's known that its work is done on an item by item basis, so it can be converted into a lazy into a lazy adapter. On the other hand, I don't think there's a generic way to do it. I don't think there's a generic way to just take an algorithm using some coroutine or some extra magic and convert it into a lazy adapter. So I have to implement my own operator plus plus, etc., and do whatever works I need. And obviously there are details that are different for each and every operation. Happily, performing the begin operation in constant time is typically very easy for most sorted range adapters, but specifically intersection and difference have the same issue that filter view might have, where it can take a long time to find the first item that needs to be outputted, and that might mean that I need to do some caching. The iterator category, if the input of all these adapters, all these algorithms, it can be just an input iterator, just a forward iterator. A single pass is enough. And if the input is itself a forward range or bidirectional range, then the result of the adapter can also basically be forward range or bidirectional range. If I'm using some sort of a heap object, I might need to create a second one for the steps backwards. Okay, if I want to take a step backward, I need a heap that's different than one for forward steps. If my input is random access, then performing a set intersection, set union, etc., cannot be remote access on its own, but I can make some use. I can potentially use the lower bound algorithm to try and improve the performance of my own adapter, but I cannot preserve random access. I cannot be random access even if the two ranges or the multiple ranges I'm trying to merge or intersect are random access on their own. If the inputs are common range, all the inputs are common ranges of the same type, then this adapter can also be a common range. And only the merge operation can preserve the sized property of the input ranges, because both intersection, union, and set difference, their size is different from the sizes of the inputs, and I cannot know it in advance at constant time without doing comparisons, but the merge keeps the exact size as the total of their inputs. And again, if I have more than two inputs, then I need some way to create this heap, and I need some memory for it. So if my number of inputs is known at compile time, it is like variadic functions, I can use like an array of variants to keep that information. If it's dynamic, I need some other way to hold the information. I might need to ask whoever calls me to give me some random access container as an extra argument that I can use to hold the heap, or I need to take some PMR allocator. The D language has a neat mechanism where it can actually make use of the storage that's inside the owning view. So if I know that there's some owning view, sort of like a temporary range that was created, and instead of being destroyed, it got copied into this entire flow diagram, then the D language, the merge operation can basically take that owning view and use that as extra memory for the heap. An alternative approach to doing all of this and writing our own classes is using std_generator. Okay, std_generator is a coroutine-based mechanism added in C++23, where I can basically just run over the input views or input elements and perform either the merge or the intersection, etc. And whenever I get an item that I want to generate as a result, I just use the co-wheeled coroutine, which is very, very cool. It's very, very simple. All the intermediate states is just variables. I don't need to think about objects and lifetimes, etc., etc. It's very, very procedural code, very, very similar to the STL algorithms that already exist. Again, I don't think it can be automatically generated for existing code, but it's not very, very hard. And the main disadvantage is that the generator is only an input range. It's not forward or back or bidirectional, etc. The performance is very, very compiler dependent and optimizer dependent, and I don't have a lot to do with it. So that's another way to do it. And we're getting to our last slide here, where I just want to tell you that the ranges library is indeed really a great library and a great achievement in terms of composability, and the fact that they've the library and the language gave us a very, very rich tool set of things that we can compose. Doesn't mean that we need to stop there. They also made it relatively easy for us and to methodically create our own objects and tools into our toolbox. And implemented it. It requires know-how. It's not very, very simple, but it's also not rocket science. Just need to follow it step by step. And now it's your turn. So really, thank you very much. I'm happy to take questions. Yes?
Regarding the random access to index of some container, I think it basically defeats the concept of the iterator, which is my experience is sequential access to some container, no?
Okay, so the question is that random access defeats the purpose of...
That random access may make it not feasible or very hard implementing iterators. Allow access to randomly to some container.
Okay, so there are some algorithms, especially for sorted information, that can be very, very helped, or it can be very, very beneficial to give them random access inputs, because they can do like all these types of binary searches. And for that reason, there's a lot of motivation if my input as an adapter is something that's random access, to also expose it and make use of it. But you're very, very right on one hand that sometimes it's not possible. It might not even be worth doing it. And on the other hand, obviously we know that jumping through memory, although in some cases it's very helpful, in other cases it can be a penalty for performance because of cache locality issues, etc. I hope that answers your question or comment. Any more questions? Yeah. Okay, so the question is regarding the overhead of the owning view. And yes, if you always use L values, then the owning views will not be created. On the other hand, again, the overhead should not be that expensive. But there is an assumption that move operations on containers and on ranges, especially if there is very cheap on its own. Any more questions or comments? It's the end. The last lecture of the day, last lecture of the conference. So really, I had a great time. Thank you so very much. I really hope to see you here next year, and come to the meetup every month, either in Haifa or in the Tel Aviv area. Thank you so much.